the divergence value must be positive, or it going inside to this solid. For this part, we call it negative. Okay, the divergence negative, while for this one, the divergence positive. Okay, another operations we have here, the curl. The curl basically relate to the rotational properties of the fluid or the vector field at a point. So in it a way on which the point here rotates. Okay, whether it rotates, okay, we have the point, the way it rotates here should be counterclockwise. So you mean that one related back to the curl of vector field. Yeah. So I have this one video here on the vector, on this what we call the divergence and also curl. Okay, you guys can see it, right? Senyap je you all. Okay, so this is like the intro, what is the divergence and curl. Okay, it's okay. Later, maybe you guys can see the video lah. Okay, in the YouTube to get what it means here by the divergence and also about the curve. Okay, because we are going to use that two properties here for the next two theorems. Okay, later maybe you can watch it lah. Maybe because BBP here cannot support like big size of the data. Okay, so then now we want to like calculate it about these two. How we want to calculate it, because this the operations is same like gradient. So we want to proceed on how to calculate this divergence and also this curl of vector field. So now the first properties operation. Given your vector field f, you have the x component function f, your y component of function g, and also your z component. Okay, k here meaning z component lah, correspond to z axis. Then we define the divergence of vector field f equivalent to, okay, we learned about this del, which is this is the del previously. Divergence equivalent to del dot product with your vector field. So differentiate this part, you will get differentiate your x component respect to x plus differentiate your y component respect to y, and also differentiate your z component respect to z. Okay, dot product must be a scalar number. Here we have scalar function. So define at all points at which all the indicated partial derivative exist, then you will get the divergence of your vector frame. Here you get divergence function. So at certain point, just substitute the points, you will get the divergence value at that particular coordinates or particular points. Okay, if divergence positive, meaning it diverges. If divergence value negative, it going to that point lah, then you get the negative. Okay, so examples we have here. Compute the divergence for these following functions. Your vector field is x square y plus 2y cube z for j plus 3z. Okay, so the formula for this divergence is del dot F. Okay, you differentiate your vector field, okay, according to these variables. So this is basically your F, this is our G, and this is the H. So you need to differentiate this F respect to X and differentiate G respect to Y and differentiate H respect to Z. So you should get lah. Here you have X square Y, so you get 2XY. This one differentiate respect Y, you get 6 Y square Z, okay, plus, and then you have differentiate this respect to Z, we get 3. Okay, that for the divergence. So you have the functions there, function that represent divergence of your vector field. Okay, this is the function lah. So depend on the coordinates x, y, z, you get the value for this divergence. Okay. Okay. That's how you calculate the divergence. The next one, we have one more, which is the curl. Okay, what is the curl? Okay, the curl, you still have a vector field. Any problem tak? Okay, for the curl, it relates on how your points they rotate. Still, you have the vector field F, G, and H component that correspond to X, Y, Z. Then we define the curl given by del cross product of your vector field F. So if the dot product, that one we call divergence. Previously, we have dot product. Okay, dot product, we get the divergence F, while the cross product of del with the vector field, you get the curl of your vector field. So define at all points at which all the indicated partial, so it can be differentiate. Curl of a vector field, we have a vector quantity. Okay. So example, compute the curl of the following. You have the f given by the function xy, and the second f is y minus x. So we do for the first one. Okay, in order to get the curl f, you have same lah, ijk, component, differentiate respect x, differentiate respect y, differentiate respect z. So here we have xi, so meaning the x component is x, yj, so the y component here is y no k here, that means 0k, plus here should be 0. Okay, then you just apply like for the determinant. So differentiate 0, meaning differentiate 0 respect to y minus differentiate y respect to z. Okay, for this x, and then you do the same for the y component also. Okay, this one I think you already familiar lah. Okay, differentiate 0 respect to x minus differentiate x respect z, but here since the sign should be negative. And lastly, for the z, you have, okay, differentiate y respect to x minus differentiate x respect to y. Here 0 respect to y, you get 0 lah, because 0 no variables y, minus differentiate y also no variable z, become minus 0. Then negative differentiate 0 respect x also 0, respect x, differentiate x but respect to z also 0. And last here you have differentiate y but respect x you get 0, minus differentiate x respect y also you get 0. So the vector is 0, 0, 0. This is the curl for the first question. Okay, 0, 0, 0. Okay, so how about the second one? We have f equivalent to y. So this one, if you want to write in the vector form, you have y, you have negative x, you have 0. Because no k, meaning k z component is 0. Okay, can you try the second one? What is the curl? Here already given answer 0, 0, negative 2. Do you get the same, which is 0, 0, negative 2? Dapat tak? 0, 0, negative 2, meaning the curl for this vector field is equivalent 0, 0, negative 2. Okay, so you should get the second part here. The answer should be 0, 0, 2. So you do the same lah. Okay, you do the same. IJK. Okay, you have IJK. But now you have y negative x 0. Okay, so here differentiate respect y, you get 0, minus this one differentiate respect z, also 0. Then 0, also differentiate here also 0. And differentiate this x respect to x, you get negative 1, minus differentiate y respect to y, also you get 1. So then from here we get 0, 0, negative 2. Okay, this one that's been the curl for this function, vector field. Okay, we also have this Laplacian, but this one we cover this on the complex function. Okay, complex function, but okay, the Laplacian, The operator that result by taking the dot product of the del operator with itself, it is denoted by the del square and it's called the Laplacian operator in the rectangular coordinates. Okay, the del square is equivalent to del dot del, meaning you just do the dot product between these two del. This also equivalent to you differentiate twice your function, and because we know dot product, it must be a number, a scalar function, not a vector. So you meaning you differentiate your function respect to x 2 times, respect to y 2 times, respect to z 2 times. Okay. Okay, this application, okay, this is what we call the Laplacian, and when it equivalent to 0, this one we call the Laplace equation. So maybe you will encounter this later lah in your field of study. Okay, the example of it, maybe you can see in the potential function for a inverse square field. So later you see in your operation lah. So example, this one compute the Laplacian. So the Laplacian, it should be the power 2 of your function phi here, which is equivalent to you differentiate here your phi respect to x 2 times plus differentiate here phi respect to y 2 times plus differentiate here phi respect to z 2 times. Okay, you differentiate your function here respect to x 2 times plus respect to y 2 times plus respect to z 2 times. Okay, now we start with the first one where you differentiate respect to x 2 times. Okay, so your phi is x is 1. If you want to simplify it, equivalent to pi square root 2 exponent x multiply exponent 2y multiply exponent negative 3z. Now you want to differentiate respect x. So here is your variable x. So exponent x differentiate always exponent x, while the rest here, these 3 become constant. I can assume just a. So here what you have just a e x. Differentiate this function one time, you still get a e x, right? If you still remember. And differentiate one more time, you still get a e x. So meaning differentiate your phi respect x, you get a e x, same. Differentiate it one more time. Okay, because exponent x, no matter how many times we differentiate, the answer always remain as ex. Okay, so it doesn't change lah. So meaning for this, it equivalent to, okay, for this differentiate twice, your function here respect to x, it equivalent to pi over sec 2 exponent x exponent 2y exponent negative 3z. Okay, that for the first one, plus now we want to differentiate your phi but respect to y. Okay, now respect to y. What should be the answer? But differentiate twice. Okay, if respect to y, what we have now is, okay, just to simplify it, if you can straight away differentiate, it should be okay. So this is your function with variables y. So these 3 now become constant. So I denote it as capital B. So now your function is b exponent 2y. Okay, differentiate one time, you have 2. Okay, 2 differentiate, you should get 2b exponent 2y. So you know lah. So differentiate here now respect to y, you should get 2b exponent 2y. Okay, differentiate one more time respect to y, because Laplacian you should differentiate twice. So 2y you should get now 4b exponent 2y. Okay, so you just add here. For the b is pi sec 2 exponent x exponent negative 3z. So pi sec 2 exponent x exponent negative 3z. Okay, then multiply with your 4 exponent to y. Okay, this is when you differentiate twice respect to y. You can simplify the variables there. Okay, but just leave it. You just leave it like that first. Okay, before you simplify it. Okay, now we want to proceed differentiate respect to z. Okay, when you want to differentiate respect z, we only look for the function with variable z. So here what we have, this part. Okay, and this can become your constant, I think. C lah. C. So you get c exponent negative 3z. So differentiate here. Okay, now respect to z, you should get negative 3 c exponent negative 3z. Differentiate one more time. So you get 9 c exponent negative 3z. Okay. Okay, so just rewrite back here. You should get the same 9 exponent. So this you put lah 9. So this the rest here for your exponent negative 3z, and where your c here is pi over sec 2 exponent x exponent 2 y. Then we just simplify your function. Okay, we simplify it. What is our common terms? Okay, at least please simplify your function. Okay, if you see here, our common is exponent x exponent 2y exponent negative 3z. Okay, exponent x exponent negative 3z exponent y exponent 3z exponent x exponent y. So your this one you can factor out exponent x exponent 2y exponent negative 3z factor out. What we have is pi over sec 2 plus here 4 pi over sec 2 plus, for this one you have 9 pi over sec 2. So this inside this bracket equivalent to 14 pi over sec 2. So finally, the final answer should be 14 pi over sec 2. Exponent this can be rewrite as x plus 2y minus 3z. So this is basically the final answer for this question lah. Okay, the Laplacian of the scalar function. So we get a scalar function also here. Boleh. So this is the answer. Okay, 14 pi over sec 2 exponent x plus 2y minus 3z. Okay, if you confuse how to differentiate, try to take the functions with the variables that you interest to differentiate lah. Okay, ada soalan? Tak ada ya? Okay, if the Laplacian is applied to the vector field, meaning you need to differentiate each. Okay, example previously we only differentiate one. Example previously only differentiate only one function, but now since for the vector you have 3 components correspond to x, y, z, you need to do for each of these lah. Okay, you need to do for p, complete for p, and then you do for the q, complete for q, and then you also do for the r. Then you just add the 3. Okay, examples now we have 2xy. So your f is 2xy. Your g is z minus 2y. Okay, I use the same PQR lah until you confused. Okay, we use the same notation. So our p is 2xy. Our q is z minus 2y. Our r is 3z square. Okay, P component, Q component, R component. So you need to differentiate this twice. Okay, the del square P is differentiate p here twice, respect x square, differentiate p here twice, respect y, and differentiate p here twice, respect z. Okay, we do for this part first, for the p component. Okay, so differentiate here, okay, we only do for the first one, respect to x. Okay, respect to x plus respect y plus respect z. Okay, what we have, respect to x, you should get proper. Respect to x, you should get, okay, here vector first lah, it's not complete yet. Okay, you should get 2y, respect y you get 2x, and respect z you get 0. Then proceed one more time. Okay, differentiate here now. Okay, differentiate this part, respect x becomes 0, plus differentiate here, respect y becomes 0, plus differentiate here, respect z becomes 0. So your answer is 0. This one, the answer should be 0. Okay, so this Laplacian f, the first component here is 0. Okay, because it equivalent to, okay, this one equivalent to differentiate twice p, okay, your q and your r. So for the first component, we already get this equivalent to 0. You differentiate respect x, respect y, respect z, then you add all the three. Okay, you can proceed here. This one also we should get 0. Only this part we get number. Because you see when you differentiate 2 times, at least the variables must have up to power 2. Then we can get number. If here all power 1, obviously later you will get 0. Okay, this one also q, you should get 0. But for this part, we will get some number lah. Okay, let's try for the r. Okay, just differentiate 2 times. Okay, just differentiate 2 times of the r here, respect to. Okay, now differentiate your r. 2 times, respect x, respect y, respect z. So if differentiate r, respect x, 1 time you get 0. So 2 times also you should get 0, this part. 0 plus. Differentiate r, respect y also, since no variable, you should get 0. But differentiate r here, respect to z, 1 time, you should get 6. 2 times, you get 6. So here plus 6. So answer should be 6. So this part should be equivalent to 6. Okay? Boleh? So this one we just go through lah. Okay.
Doktor, y tak 6y.
Y tak 6y, yang mana satu
R. Z.
6z, because it's just z, we differentiate respect to x, y, z, right? Bila tak ada that particular variable, so dia become 0 lah, because it's, we consider constant. Okay?
Oh.
About the curl, later we cover more in the Stokes theorem, because the properties tu basically it, the behavior of it rotational, the axis of the rotational tu yang kita dapat by using the curl formula. Okay, so maybe you guys can take a break for 5 minutes and before we proceed with the Stokes theorem. Okay, Stokes theorem. Take 5 minutes break. We start back at 8:50.
Madam?
Yes.
And is this topic released in Ulan? The slide.
That one under the vector function. But
Okay.
in the slide there, it just like, I think there's a few yes, we have this in the Euler lah for the curl divergence, but for the Stokes and the divergence theorem, it is under the vector function.
Vector function. Okay.
Under vector function.
Thank you, madam.
Okay. Okay, for Muhammad Daniel, you ask me why the dx dz or dy dz just not equal to 0, because we don't have the z component on your x function. Okay, that's why bila it become constant lah, because if you interested to differentiate respect to z, but your function no variable z, then it becomes 0. Okay, they become constant. Okay, we only interested with our variables. Example, kalau you nak differentiate respect to x, your function, if no variable x, it becomes 0. But if you have variable x, that you can differentiate the x lah. Okay. Okay. Alright. So now we go back to, we proceed with the second theorems, the Stokes theorem. Stokes here basically same like green, but we project it into 3-dimensional. Okay, into 3-dimensional. Okay, so Stokes theorem. Okay, now we proceed the generalization of Green's theorem to 3 dimension that has important field. Okay, this one just the intro. Okay, this is the Green's theorem relate in 2 dimension. Okay, we only have x, y variables here. But now if 3 dimension, you still have surface here. We learned about the surface integrals already. But now okay, it's same as the Greens, you check the, the line integral here, counterclockwise, but only in 2 dimensions. Okay, so it said here the line integral for this function also equal with the, okay, you integrate the area of this, okay, but we have this formula, right? But it should satisfy this part. Okay, this one basically it equivalent to the curl formula if you but respect to z constant. You should get this formula. Okay. In 3-dimensional like this about the Stokes. The Stokes theorem, it relate the line integrals but over 3 dimensions where we interested, okay, this Stokes theorem relates surface integral over a surface. So you have a surface now in 3 dimensions to the line integral. So it's same if you want to get what is the line integral here, but now in a 3-dimensional, you need to consider what is your space function here and denote it should be same, must be counterclockwise direction. And you have here the direction of your field should be pointed upward. Okay, this one you call the right hand rule. Okay, because if you go to this direction, meaning it must go pointed upward. Okay, we have the right hand rule. If S is an oriented surface bounded by simple enclosed, same with green, it should be simple enclosed, then the positive direction of your curve C establish a right-hand relationship between the orientation of your surface and your contour C. Okay, it should be counterclockwise direction. Okay. Okay, so Stokes theorem state that the surface integral of your curl. Okay, now you want to integrate your surface but corresponds to the curl is equal to the line integral of that vector field over the surface function. So basically, this is the line integral formula. Okay, the line integrals for your closed surface. Okay, basically this one equivalent to the curl of your function dot product with your normal. This one we call normal. The normal of your surface function. Okay, this is our surface lah. S correspond to the surface. S here is surface function z equal to function xy, and n here is the unit normal vector of your surface S. So this n basically equal to your gradient function. Okay, your n here equivalent to gradient function del f. We already get this one previously. So this is what we call Stokes theorem. Okay, we just go to direct to the formula. So the line integral for 3-dimensional, Okay, also equivalent to the curl of your vector field dot product with the gradient of your, this one we already know, this is basically the gradient function, del gradient of your surface, z minus f. Z equal to your fxy is a surface function. Okay. So if you don't want to apply the Stokes theorem, you can apply this formula previously that we learned, where you need to translate your function into the t form and you apply the line integral. Everything should be in terms of t. You get your interval for t and you differentiate, you integrate. Okay, one of the example of the usage of Stokes theorem is to find the work performed by a force field on a particle that travels a simple closed piecewise smooth boundary C in the direction that can be obtained by integrating the normal component of the curl over an oriented surface bounded by C. Basically, if you want to find like what is the, when you travel along this closed curve C, what is your total work done? Remember, the line integral also equivalent to work done. Okay, imagine you travel along this C, okay, but you have this vector field F here, okay, that you need to go through. So that one equivalent to your total work done. This one also basically equivalent to the total, the curl of this surface lah. Okay, it said it must be equivalent with the curl of your surface function. Okay, so how to compute the Stokes theorem? This is basically the steps. One, you need to calculate your curl. The formula for the curl is del cross product with your vector field. You must have this capital F. This one is your vector field. Second, please choose your surface because you need the surface here. Okay, with the boundary C. Boundary C, that this one will determine your area. Okay, in two-dimensional. Determine the projection of D on the XY plane. This is relate back to this one lah. Okay, the XY plane, the area that you need to get the boundary of it. And the last one, find the appropriate limit. This one based on this lah. Okay, all these three basically in order to get your boundary. Okay, remember you need to get this boundary. This one correspond to the XY plane. Okay, example. This is your surface lah. Example that you, okay, this is the surface. Okay, and you go along this boundary. Okay, this is your contour C. It should be counterclockwise. Then you get the right hand rule. Okay, then if you project it down here, you get like some region. Okay, this region is the area or this part that you need to get the limit for your surface here. This one same like the surface integral. You need to get the boundary for this surface when you project it onto the XY plane. So examples now, we want to evaluate the curl using the Stokes theorem. Okay. Alright. Kita buat yang ni dulu lah. Okay. Why? Because this one kita circle. So we go back to this one without circle. Okay, given the vector field F, where S is the portion of the plane in the first octane with the upward orientation. Remember, it should be upward because we want to make it counterclockwise direction. Okay, if basically for the Stokes it should be positive. Sometimes we call it positive orientation, sometimes we call it upward orientation, sometimes we call it counterclockwise. That three means the same thing. Whereas here is the portion of the plane, so this is your surface. Okay, now you have this surface. As how to draw this plane? Okay, this one plane meaning flat surface. You can substitute example x and y 0, hello, z1, x and z 0, so y1, y and z 0, so x1. What you should have is, okay, what you should get, basically you have this point 1, 1, 1. It said first octant only, so no need to project it to the negative axis. So this is basically your plane. Okay, should be straight line here. This is your plane. Okay, and if you project it, okay, if you project it onto the XY plane, normally you akan dapat this area lah. Okay, you go to the two-dimensional. What we have is 1, 1. This is your X. This is your Y, and this should be the area when you project the green plane here onto the XY. So you need to get the limit of this because you need to get the limit for your intervals. Okay, that one depend on this region of XY plane. I think this one you should know already. Okay, if I want to start dx dy, okay, if I want to do it dx dy, okay, if I want to dy dx lah. Okay, dx, I take x 0 to 1. For the y, I need to get the lower boundary. So here, this value, so y 0, but the upper is a line. So I think you already know how to get this line function. Okay, y equal to negative x plus 1. Okay, because same as yesterday example, on Monday example. So this is your boundary. So the boundary now complete. But now we need to, because we want to apply the Stokes theorem, because three-dimensional, you need to get inside here, the function inside here, which is curl. It is the curl must be dot product with the divergence z minus f. Okay, so now the boundary complete. We just want to proceed with the first one, which is the curl f, and the second one, the gradient or the del of your surface. Boleh? Okay, the boundary now complete. So in order to get the first one, the curl f, which is equivalent to ijk, differentiate respect x, differentiate respect y, differentiate respect z. Remember, because sometimes you might be confused which one is the surface, which one is the vector field. The one with the vector notation here is your vector field. So this one lah yang you kena differentiate, x minus y, and then y minus z, and this one z minus x. Okay, get the curl of this. Boleh? Guys. Okay, basically for this, okay, if you can okay, so differentiate. Now, I think this one you should know lah. Okay, now we want to differentiate this part respect to y, but no variable y, it becomes 0. Minus differentiate this respect to z. Kita ada y minus z, y becomes 0. Minus z, z differentiate z, we get minus 1. Okay, that's for the first component here. Okay, how you get the curl. Remember, the notation plus minus plus, so that's why now we have negative. Okay, now we want to proceed with the second one. Okay, we want to now differentiate corresponds to the second one. Y, remove this part. Okay, now differentiate here. respect to x. Kita ada this one, negative x. Z 0. So 0 minus 1 minus, differentiate this part, this x minus y, but respect to z, since no variable z, meaning minus 0. Okay, now the last part here. Okay, now look for the last one. Okay, differentiate y minus z respect x. Tak ada variable x, then it becomes 0. Minus, differentiate now x minus y respect to y. Differentiate x, you get 0. Forget, we have negative sign here. Nanti you forget the positive negative. Minus y, so minus 1. So if you simplify this, negative negative, what we have is 1. This one also positive 1. This one also positive 1. So this is our curl F. Okay, so for this part now done. Number 1 done. The curl F equivalent to 1, 1, 1. Okay, 1, 1, 1. Now we want to find the gradient. Okay, this part. The gradient of your Z minus F. If you notice, it should be Z minus, it should be just Z equal to function xy or Z minus function xy equal constant. Everything should be in the Z side and Z here should be positive. Now this is your surface, already Z positive. You just need to differentiate this part to get the del F. Okay? Pening dah ke? Okay? Boleh? So, what should be your Z? Okay, now, so our surface equal to Z plus X plus Y equal to 1. Okay, this one lah. So now we want to find the Z minus Fxy, meaning Z here should be positive. If you look here, Z already positive. So this is equivalent to Z plus X plus Y equal 1. And you need to get the gradient of this. Not gradient F, do you confused? Okay, gradient of this Z minus Fxy, where it equivalent to differentiate respect X plus differentiate respect Y plus differentiate respect Z. Okay, so this what you need to differentiate basically is this one. So basically this part lah yang you kena differentiate. Okay, now if you want to differentiate respect X, we have X here become 1 plus differentiate respect Y, we have Y here 1 plus differentiate respect Z, we have here 1. So this is equivalent to 3. Okay, this one equivalent to 3. So now we take this function, this part now equivalent to 3. No, this, sorry. So this should be the vector lah. Okay, you should get vector form, not the del should be vector form. Okay, so we have here basically vector 1, 1, 1. So the previous one, this should be 1, 1, 1. This part also 1, 1, 1 from here. Okay, so you do it, you get the answer. So what we have now is 1, 1, 1 dot product 1, 1, 1 of your area where y from 0 to negative x plus 1, x from 0 to 1. Okay, this is curl F, this is divergent, not divergent, del of the z minus fxy. Boleh? Ke pening? Okay. One differentiate dapat 0. Yes, depend lah because one constant, right? So should be 0. So then if you just substitute everything into the Stokes formula, okay, then we get here, you proceed with the dot product. Basically Stokes theorem ni you need to do 3 things. One, get the curl where you need to apply the cross product. Second, you need to get your gradient where you apply the dot product. And the third one, you dot product between both your answers. Okay. Alright. So here you should get you should integrate 3. Okay. If you proceed back with this function, you proceed the dot product. What you need to integrate basically your area 3 dy dx y 0 to negative x plus 1 x 0 to 1. You get lah the answer. Answer dia berapa? Answer is 3/2. Okay, this one only because what if you refer to our drawing previously, we have this plane. Okay, dia tak involve related to circle. I'm not sure slide in the tube whether you use circle or not lah. Okay, like this. Okay, and when you project it, when you project this into the XY, you akan dapat just this. Where this one yang you kena write here in this, you kena write in this surface. Basically, what it means here, when you travel along this surface line here, okay, you travel this. What is the line integral along this blue line here? Okay, this one also equivalent to the curl of your surface. Okay, where kat luar ni kita ada vector field. We don't know what is the direction of your vector field. And the direction of your vector field, meaning what is the total work done if you go, okay, kita guna color hitam. Okay, this one is your vector field lah. We don't know lah, maybe direction like this, we don't know. Okay, but this represent by the capital F previously. Okay, you move along this blue line against this vector field. What is total work done? You can apply the Stokes theorem. Okay, where you get the curl of your vector field, the gradient of your surface, and then you dot product it, you get the functions, then you integrate. Okay, it should be this one basically the gradient lah. This one we already covered previously. This is equal to gradient, meaning gradient of your surface. It should be pointed upward. Boleh? Before we proceed with the next examples, boleh tak? We go back to example 1. Example 1 tadi is part of circle. So if you remember back, part of circle, you kena guna polar coordinates. Okay, how do we get 3? You apply the dot product. Okay, we apply the dot product. Okay, yes, previously the dot product is x component multiplied. Okay, I choose different guy. Okay, the x component, so 1 multiply 1, we get 1 plus y component 1 times 1 plus 1 and z component 1 times 1 plus another 1. So we get 3. Okay. Okay. Okay, so then you can proceed here. Answer is 3/2. Do you get the same? Dapat tak? Negative x plus 1, negative x square. So negative 1/2 plus 1. 1/2. So we get 3/2. Okay, so next as previous example that we skip about the circle. Okay, this one, evaluate curl f dot ds using Stokes theorem given your vector field f where s is the part of the paraboloid z 9 minus x square minus y square z equal 5 oriented upward. Okay, maybe this one you can try. I just give you the brief, okay, the intro. Yes. Okay, so basically you have the vector field. But remember, this vector field is where you can get the curl f equal to curl cross product f, and this is your surface. But if you notice in your drawing here, you might be confused. Okay, now I just draw z equal 5. Okay, z equal 5 meaning this is x, y, z. So z5 meaning you have this 5. Because 3-dimensional, you don't just get line, you get surface. Okay, you get surface lah. Surface, or you get plane, where this plane must be parallel with z axis. It must parallel with the xy plane and intercept the z here at 5. That's what we call z equal 5. Okay, it must intercept z at 5. So this is z equal 5. The second one, we also have, it said s is the part of paraboloid. Okay, and the second one, we have the z equal 9 minus x square minus y square. This is the second part. Okay, I draw it another, okay, I draw it here lah. So later we combine. Okay, you learn already parabola, right? Parabola. Okay, example I have. Okay, example. Apa tak boleh ni? Okay, example I have. Example y equal, because negative, I use negative sign also. Negative x square. So you know this is parabola. This parabola, 2-dimensional, negative. You know already if a is negative, less 0, your graph should be concave downward. So this part concave downward, where you have x and y, plane only 2. When you have 3, it's become paraboloid. Okay, where instead of y here lah. Now this one, we use this is we call z. Okay, we use this one where we call z. Okay, now z. Okay, this is your x, y axis. Okay, now refer to this, you have z equal 9 minus x square plus y square here can be put in bracket. Okay, because here should be same sign here. You have negative, so you know your graph or your parabola should also concave downward. Okay, but in 3-dimensional, same like this. If you have like plus 3, that means you intercept at 3. Right, but here we have plus 9, that means we intercept at 9. But parabola lah. Okay, it should be circle. So now we bring it here. Okay, we bring it to this. You have 9. Okay, so in order to get, okay, now if you look here, you have circle kat bawah ni. Below here we have circle. And we know this one same like here lah. So what is, if you have circle, maksudnya below here you ada value z is 0. Same here, you ada value y is 0. If you solve for y0, you akan dapat your intercept here. Okay, you akan dapat your x-intercept. Same here, if you substitute z0, you get your intercept here. Okay, so example for this, when z0, when z here 0, so what we have basically is a circle with radius 3, right? So here basically our radius equivalent to 3. Okay, what you have here, it should be go down lah. Okay, and this is should be 3. This part is basically we have like ball here. Okay, consider this three-dimensional. Okay, this is basically our surface. Okay, now if you combine this figure 1 and this figure 2, you notice the first figure, okay, the first figure, we have plane at 5. And this figure is paraboloid converted, is concave downward. So 5 is here lah. So kalau you combine, you have this plane here at 5. So what we have basically, if you combine these two, what you have is a macam ni. Okay, you have like this, where this one is 9, below here is 5. Okay. Okay, you have this basically, our solid. Okay, because remember why we need this region. Remember we interested to get the projection of this into the XY plane in order for you to get the boundaries of your region A. So instead of kita stop dekat 3, because we stop at 5 here, you need to get what is the boundary here, what is the value for this radius. Okay, this new radius. It not 3 because 3 here went 0, but now kita tak stop dekat 0, kita stop dekat 5. So what should be the new radius here? Okay, okay, this is your first surface. This is your second surface. You combine it, you get one solid. So how to get this radius? You can just Z1 must equal to Z2, then you get your circle here. Boleh? Understand? So if you simplify it, you should get here 2 and 2. So basically what we have is a circle with radius 2 as our area. Okay, so that's mean this area down here, okay, area below here is a circle. Okay, basically your area is a circle with radius 2. How to get these two? You solve for Z1. Z1 is this part lah. Here I denote as Z1, 9 minus H square minus Y2. Your second Z is 5. You solve simultaneously, you should get intersection, right? Remember, if you want to find intersection, meaning it must have same, if coordinate, same coordinate, if function, same value of your function. That's what we call intersection. So same here, we need to solve simultaneously Z1 and Z2. Then you can get that the radius of your circle now equivalent to 2. Okay, boleh? Pening sikit nak faham. But that's how you understand it lah. Okay, boleh? So now that is our region A. Maybe you can proceed now with your curl and also with your divergence or your gradient surface, and then you substitute into the formula lah. Okay, so since no question, I just proceed. Basically, our drawing is this X, Y, Z. So this is the Z1. Below here is Z2. Z1 here is 9 minus x square minus y square. Z2 here equal to 5. And so you need to project it here in order for you to get the area. Get this area. So now you get already. Okay. F dot product with the Z minus function xy. It is the formula of the formula of Stokes theorem. Okay, so the area now this part. Okay, this is the area A. I just bring it outside. You have X, you have Y, where your radius should be 2. Remember, because now we use the region part of circle, so better for you to use polar coordinates. Okay, but before that, maybe we can just leave this part first. Later we see lah whether this part can be simplified or not, depend on our function. Okay, this should be the boundaries of our question because part of circles. How to get this? You should understand already because circle here, okay, this line with radius 2 equivalent to x square plus y square equal to 4. So I just simplify for the y, that's why I got negative square root and positive square root. X, I take the number, so basically integrate dy dx lah because y here in the form of function. Okay, now in order to get this curve, you can apply the cross product of your del. Okay, this one, the first part. While the second part here, z minus. Okay, z minus fxy, meaning it should be your surface. If you notice, for your solid here, okay, this is our solid. Okay, this is our solid. You have two surface. Whether you use this as your surface, okay, your surface here should be bounded. Okay, bounded the curve C. Okay, this curve C. So, because this is our curve, basically this is our curve. This is the curve lah. Okay, this is our curve that you travel. So you have two options for the surface. If you look here, first you have this function of surface. Okay, so you can use Z1. Okay, sorry, I use black lah. Okay, you can use Z1. Okay, you can use this, or you also have the second option for your surface, which is below here. As long as dia mesti bounded that curve, up to you which surface function should be okay, or you can use the second Z. Okay, so this one, because remember it should be in the form of it's the form Z minus, so everything should be in the side of Z. So this can be Z minus 5 for this part, or you can use Z plus x square plus y square minus 9 for the, if you want to apply the first surface. Okay, up to you. As long as it should bound the curve C. Okay, so for this part, this one, you boleh apply the first surface or the second surface. Answer akan sama. But for me, I will choose the second one. Why? Because here I only have one variable Z. Kalau ni ada 2x plus 2y, nanti dia akan jadi, if I choose the first one, here, you will get 2x, 2y and 1. But if I choose the second one, it should be 0, 0, 1. Okay, up to you lah. Okay, but please remember this entry Okay, this entry will always 1. Okay, because Z differentiate, you always get 1. Okay, this one you only have variable x, y. These two will be different lah, depend on your surface. Okay, maybe you guys can try. I already put all the informations there. What should be the answer for this? Answer already given, which is negative pi, negative 4 pi. Boleh try this question. Get the curl, then dot product already given to you also. The gradient to x to y1 or 0, 0, 1. Depend which side you use as the surface. Okay, boleh. You should get negative 4. Okay, because here you guna circle, so I think better for you to use the circle properties. Kalau you guna circle properties, okay, this is equivalent to this one. R0 to 2, our radius, because up to 2. Because complete circle also, your theta 0 to 2 pi. Okay, so you change into the R and theta form lah. You use dr d theta. So R from 0 to 2, theta 0 until 2 pi. And make sure, because you change into the dr theta, you need to multiply with R. So just this part, you substitute from this. Boleh guys, senyap je ni. Okay, this is the answer for the previous examples. Okay, the curl F, you should get -1, -1, -1. For the gradient of the surface, I choose surface Z equal 5. So I need to find gradient Z minus 5. Differentiate Z minus 5 respect X, respect Y, respect Z for the X, Y, Z component. So I got here 0, 0, 1. Proceed with the dot product between two of the answers there. So we get -1. Then you just substitute into the, okay, you substitute it back here lah. Okay, substitute here. Okay, this part substitute here. But remember, because we use R and theta, this one need to multiply R. So what you need to integrate basically -R d theta, where R from 0 to 2, 0, theta 0 until 2 pi. So integrate this R, I get -R square over 2. Substitute the R, 0 until 2, we get -2. And proceed, integrate respect theta, we get -2 theta, put the value 0 until 2 pi. Finally, we get -4 pi as final answer. Okay?
So, madam,
Yes.
because it is circle, so we have to use dr d theta.
Yeah, kalau circle, kalau region you ada involve circle atau part of circle, you kena guna polar coordinates, and when you change to polar coordinates, make sure you kena multiply with R. Okay?
Multiply. Because radius. Okay.
Because the R there basically the Jacobian of your transformation. You transform from rectangular coordinates into R coordinates.
Okay.
What it means here, sebelum ni you guna X and Y kan, but now you guna R and theta. So you kena ada the Jacobian transformation. Okay, untuk for the polar coordinate, the Jacobian transformation is R. So make sure kena multiply with R. Okay, that's meaning the coordinates here lah. Okay, another question. So final answer here is -4 pi. Okay, so you can check example in slide given at ULearn. That one, if I'm not mistaken, they give you. Okay, what about the Stokes theorem yang kita ada in our slide? We use okay. Okay, this one in our ULearn, slide in our ULearn. So this part kita guna examples that we have here is the example that we have here is triangles. Okay, this example you boleh check dekat ULearn. Okay, and here we use plane. So how to draw this? Same like previous one. You ada 2x, you substitute x and y 0, you akan dapat z. Z here is 6. When you substitute x and y, x and z 0, y is 3, and here also 3. So this is your plane lah. Okay, so you need to get the region here. So this region is 3 and 3. So -x plus 3 is the y. That's why here we have y is, but here they use x. So meaning you just solve this one for x lah. X is 3 minus y become x. So that's why 3 minus y. Y here from 0 to 3. Okay, this is the curl. And surface, you kena guna this surface lah because it is the only surface given by this equation. So 2x plus y, so you dapat 2, 2, 1. Okay, 2, 2, 1 for the surface function. Boleh this one in your slide lah. Okay, I think there is another example. Ada tak? Okay, tak ada. In your slide, only one example. But I think in tutorial, we have a lot of other examples. Okay, I think that's all for today. If you have questions, you can ask me. But if you don't have any question, you can dismiss. But like usual, before that, make sure you send your attendance and also complete the satisfaction polls for today's lessons. Okay? Okay, so this is attendance if you cannot use the Power Apps, and make sure to sign in to do your satisfaction polls. Okay, ada soalan you may ask me, but if you don't have any question, you can dismiss. Okay, I'm planning to do quiz because we already complete chapter 2. Bila we can do the quiz like the previous quiz, it should be, we do it multiple choice. Okay, maybe this weekend mungkin tak boleh, tak sempat kot. Okay, maybe next week we will have quiz. Okay, because online I think we can do it using system lah. Okay, maybe weekdays lah. Okay, so if you complete, you can dismiss, and any question you can stay lah.
Thank you, Doctor.
Okay, you're welcome.
Madam, so the quiz will be chapter 2 only.
Yup, chapter 2.
Okay, thank you.
Okay.
Thank you, madam.
Okay, sama. Yeah, if no question, I will dismiss lah. Thank you.